and welcome to this week's instalment of Nucleus Investment Insights. This week our attention turns to the growing electrification of our world. Whilst for most of us this is probably the most noticeable in the evolution of our gardening equipment, leading the vanguard of the new era in powered by powered devices is the electric vehicle, or EV. Tesla, with the help of significant US government support, has spent the last decade or so dragging the Western automotive industry from its rusted-on adherence to fossil fuel-powered engines into the 21st century and beyond. As electric vehicles have proven to be not just the future, but the near future, more and more established players have been forced to develop and adapt their own vehicle production methods to try and stay relevant. With all emerging technologies, and in particular big tasks like redefining how our vehicles are powered, there comes engineering challenges, alternative energy approaches, and vested interests. Several energy sources have been offered as alternatives to batteries, with hydrogen being brought to the fore as a potential suitor with some noteworthy advantages on the surface anyway. But more on that in the show. To help colour in the exciting and long overdue revision of re-energising global transport, we are lucky to be joined on the line from Canada by energy aficionado Paul Martin. Paul is a chemical process development expert who currently works as program manager and senior technical fellow at an engineering firm located in Ontario, Canada. He has written extensively over the years on the various use cases and potential for alternative energy sources, and has even converted his own car into an electric vehicle as a proof of concept. Paul Martin, welcome to Nucleus Investment Insights.
Pleased to be here.
And also joining today's thoughts on the future of vehicle energy and relevant impacts to our portfolios, we have Nucleus Wealth's Head of Investments, Damien Klassen. Hello to you, Damien.
Hi, Tim.
And just a quick reminder before we get started, if you haven't already, please subscribe and click on the notification bell to be notified of when we go live or have a new webinar to watch, or follow us on your preferred podcast platform. We also ask if you'd like to take a moment to click like on the video now to help our show grow. So we'll kick off today with a broad agenda, and I feel we're covering a broad series of topics today. And they're all very fascinating. But what we're sort of roughly, as a guide for those listening in, we're going to kick off with the Elon Musk quote. We're then going to have a look at hydrogen. Is it the future or is it a farce? We'll then dive into lithium. Is there enough? And chat around, of course, that very important component of what we're talking about today. And then finally, rounding out in a battery tech update, both present and the future. So on that note, I'll hand over to Damien to get the ball rolling.
Yeah, so thanks a lot, Paul, for coming on. I mean, the main reason we wanted to get Paul on is we're trying to get this. There sort of seems to be very much two sides to the whole electric vehicle equation. There's the people sort of coming from the fossil fuel stage who are like, no, this stuff's never going to work. It's, it uses up more, and you don't have the whole life of, it doesn't take into account all these other factors, and so that's not going to, it's just not going to get there. And then at the other end, you have the, some of the religious converts who are basically saying this is all magical and it's fantastic, and they probably extend it in the other direction a bit too far. And so what we're really trying to do, and what the real reason for getting Paul on, is to try and get this a bit more realism behind it, and sort of put together some of the timeframes and really to look at what are the key things we should be watching for. Because for me, it's there's so much uncertainty around a lot of the technologies and when they'll reach the right levels, but knowing where the main things to be watching, because there are so many things going on. And so that was where, Paul's got a number of articles out on LinkedIn debunking both sides of the argument. And so, I thought it'd be great to have him on, especially around solid state batteries. That's where I want to get to in the end. But I think, given we've got him on, I feel remiss if we don't sort of hit him up on a few of the things he's sort of posted on. So I might start with this. As I said, Elon Musk came out with a quote, basically saying, Well, let me read it out. You have enough electricity to power all the cars in the country if you stopped refining gasoline. You take an average of 5 kilowatt hours to refine gasoline. Something like the Model S can go 20 miles on 5 kilowatt hours. And so you basically have the energy used to power electric vehicles if you stop refining. So, I mean, that was one. I know I sort of hit my bullshit detector, but Paul, it also hit yours.
Mine too.
And you've
It
written
really
up.
did.
Yes. So do you want to jump into, what your thoughts are around, if we just stopped refining, could we all of a sudden have all this enough electricity to run every car?
Well, I like to be brief when I can be. So the answer to that question is absolutely not. And our friend Elon, who I have a lot of respect for what he's done, he does kind of occasionally go off. And in this instance, what he's done is he's sinned against thermodynamics. He's committed the first sin of thermodynamics, as I like to call it. Um, your listeners might be aware that there's energy, and energy is energy is all denominated in energy units, joules or kilowatt hours, as an example, or BTUs. But energy is not created equal. There's a difference between heat and work or mechanical energy. So chemical energy is basically the equivalent of heat, and mechanical energy is the equivalent of thermodynamic work. And electricity is a currency that can be converted very easily to thermodynamic work or mechanical energy. So just because they have the same units doesn't mean that they're worth the same. There's an exchange rate. It's like the difference between, say, Canadian or Australian dollars and American dollars, or Jamaican dollars for that matter. There's an exchange rate. And if you screw up the exchange rate, which Elon's done with that quote, you get the answer wrong. So the reality is this: the energy that it takes to take um, the energy in petroleum to gasoline or diesel that you put in your tank. Round numbers, that process is about 80% efficient from discovery and the well all the way to the tank. So it's about 80% efficient. So about 20% of the energy in the petroleum barrel is lost. It's used in the process of transport and refining and so on. But the problem is you can't say, okay, well, 20% of the energy is this many kilowatt hours, and that's enough to drive your car 20 miles, because that's just plain wrong. Uh, the reality of the situation is that only about 15% of that 20% of the energy that's lost is used as electricity. 85% of it is used as fuel gas in the refinery, and it comes right from the barrel of petroleum, or maybe it comes from natural gas. It's byproducts in the refinery that are burned, et cetera, et cetera. So really only about 15% of 20% of the energy is used as electricity. And that might move your car 3 or 4 miles on the same basis. So, on a gallon of gasoline, whereas a gallon of gasoline might take your car, it'll take my Prius, almost 50 miles. So wrong by about a factor of 10.
Yes. That was where that's on that one. I could work back the other way. How much the refineries, how much electricity do all industrial companies use in the US, and then how much the refineries use, and then you work back the other way, and you just this doesn't add up.
Yeah, it's
decimal
really
point
tough
out.
when you try to do it. Like I've done it as accurately as you can possibly do it, because it's kind of my area of expertise, being a chemical engineer. So I dug up this. There's this model that's produced by the Argonne National Laboratory in the US called the GREET model. And the GREET model is kind of the gold standard for figuring out how much energy is in stuff. And in a refinery, you have to do that super carefully, because there's all sorts of products. There's gasoline and diesel, but there's also jet fuel, and there's lubricants, and there's plastics and chemicals and all manner of stuff that comes out of a refinery. And you have to take it all into account. So to distill it down to the point where you have a gallon of gasoline, it's tough to do. And Argonne, they're the experts. They've done it. And I've actually checked it against the similar publication that came out of the EU, and the numbers are almost like dead on, which is shocking. But yeah, it's round numbers, 80% efficient from well to tank, And then, your real problem with a gasoline or a diesel engine isn't from well to tank. It's from tank to wheels.
Mm.
That's where you lose the energy. And
Yeah.
that's because you're trying to take chemical energy, which is heat, and you're trying to convert it into work. And thermodynamics, the second law says, hey, pay up, buddy. That is a tough transition, and it's not an efficient one,
Mm.
especially in small engines. So,
Mm.
we do that not because it's efficient, we do it because it's effective. The trouble is global warming has kind of, killed it for us. And so
Mm.
we've got to do something else.
Yeah, and then I guess putting that into numbers, I guess you spoke about a Prius, I think sort of about 30% efficient, I think, if I'm right, and most
Yeah,
cars
Prius,
is probably like 20.
it is a bit tricky to get real numbers there because a Prius is capable of maybe 40% on the lower heating value efficiency, from the tank to the end of the motor shaft. Um, so but that's peak efficiency. That's not the average efficiency of driving the car and having the engine sometimes run when the car's stopped just to keep the engine warm, which even a Prius will do. Um, but by the time you take it from energy source to wheels, for a Prius, it's round numbers about 30%.
Mm.
And for a regular car, it's about half that. Fleet average car is about 15%. 15%. It's pretty
Mm.
lousy. So
Yeah.
EVs on the same basis, they're closer to 77%.
Yes, and so
So,
that
that's the reason they're so awesome. Well, that and the instant torque when at 0 RPM, which, if you're a car guy, it's intoxicating. So, from the pure love of cars point of view, when I converted my little British sports car to an EV, the fact that I could sit at a stoplight and step on the accelerator and I got more torque at 0 RPM than that car had at 4,000 RPM with a gas engine in it. That was just wonderful stuff. And the fuel economy or energy economy and the greenhouse gas emissions and the toxic emissions reductions, that was all just beautiful gravy as far as I was concerned. That the
Mm.
instant torque is just beautiful, and the silence.
Mm.
You know,
Yeah, well, and I think that's the one where it's the question about when people get over that range anxiety part. But to me, it's really a cost thing about when people can look and say,
oh yeah,
like we had this thing with light bulbs in Australia where they basically were going, okay, we want to convince everyone that stop using your old incandescent ones that are very cheap but burn out really quickly and switch to these other ones that last much longer but they cost a lot more, and people wouldn't do it. And eventually they just had to ban because they'd turn up and go, oh, do I want to pay $2 for a light globe, or do I want to pay 20 cents for a light globe? And you go, oh, I'll take the 20 cents.
Yeah.
And despite the fact you're going, no, the $2 one's going to last you like 100 times longer. And so
yeah.
eventually they just had to go, no, you can't have them anymore. So
That's the trouble with people, right? I mean, we sometimes we're like kids, and we just have to be told, you have to smarten up. You could have all kinds of nice things if you were just smarter about it. And that's the trouble, is that people sometimes they talk a good game about thinking about the environment and even thinking about their own pocketbooks. I mean, that's the reason every Canadian converted their house to LED lights, was to save money, because electricity is not cheap. And
Mm.
so, yeah, sure, your LED light bulb costs more than an incandescent, but it's giving you way more light per unit of electricity consumed, and electricity is not cheap here. So when you do the math on that, it's pretty simple math. I'll tell you, I got the incandescents out of my house in a big hurry, and I bought a lot of LEDs when they were quite expensive. But they were subsidized as well by the
Mm.
local electrical authority here, and that was a good policy because it got the incandescents out of those houses and got people over the worry about spending $15 on a light bulb as opposed to spending 50 cents.
Yeah, and I guess it's that part then with cars is when I sort of feel as if it needs to be quite a small gap where people can actually say, oh, okay, I'll buy the car, it cost me $5,000 extra, I saved myself, I could see I was saving $2 or $3,000 a year on petrol, and so therefore within 2 years I've got my money back. Okay, now I'm good to go. Whereas I think if it's a
Yeah.
10-year or 15-year payback, people are like, well, I may not even
Oh
own
yeah.
the car that long. Yeah.
10 or 15-year payback is not very exciting from an investment perspective, is it? And
No.
especially not your average person that's got to worry about their beer budget or whatever the case may be, the argument of lower total cost of ownership, it matters to people like me. I mean, I used to drive 120 kilometers to work and back every day, and I did that for 20 years. First 5 days a week, and then 4, and then later 3 days a week, driving 61K each way, so 122 kilometers. And by the way, when I converted that little 1975 Spitfire, that car had an 18.5 kilowatt hour battery, which is tiny. It had a range of 100 kilometers, so I could drive to work, but I couldn't get home on a charge. Okay, so but I drove that car 16,000 miles, so whatever that is, over 20,000 kilometers, uh, by plugging into a landscaping outlet when I got to work. And the only thing I ever had to worry about was if I got fired first thing in the morning, because then I'd have to hang around for the rest of the day for my car to charge up so I could go home. I could almost get home. But I couldn't quite get home because the car had, 100 kilometers of reliable range on the highway, gunning it, which is the only way to drive a Spitfire, honestly. And especially an electric one. So, but that's how I did it. I fully charged it at night off a landscaping outlet when electricity was cheap. And then I drove to work and I plugged it into a landscaping outlet at work. And, I'm part owner of my company. So as a shareholder, I don't rip my own company off. So the boss agreed to let me charge my car, but I had to pay the average cost of electricity per kilowatt hour and report it on my expenses. And that's the way that we do it with everybody. Now, the problem is that was my boss ripping me off a bit because the incremental cost per kilowatt hour is actually less, but that's not an argument you could win with Dave. Anyway, that's the way I did it. And 16,000 miles, the biggest problem I had in those 16,000 miles was my face got sore from the EV grin that I got every time I stepped on the accelerator. It was just so awesome. But the problem is, I did this in 2014. I did the conversion with my son as a project for us to learn together and for me to learn about electric cars, because I'd had Priuses before and loved them and thought they were awesome. And I wanted to learn more, and this was a good way to do it. And I drove the car, like I said, for 4 years and 16,000 miles. And then one night when I was coming home from work, a guy in a big Dodge 2500 with dual rear wheels, a giant pickup truck, gas or diesel engine, of course, changed lanes into me and totaled my car.
Whoa.
This car that I'd put hundreds and hundreds of hours into. So you can imagine I was a little disappointed. I was rather grateful to be alive, but I was pretty disappointed that the car was totaled. The good news is, though, that all the electric stuff came through the crash just fine. And I have last year, during the beginnings of the COVID lockdown, I dropped the drivetrain from that car into a 1973 TR6. And that project went super smoothly, and I'm now driving that car around. But of course, with COVID, I don't drive to work and back anymore, and I like that much better.
Fair enough.
It's more efficient. You move information instead of people whenever you can. A car is always a compromise. Dragging a ton or 2 tons of metal around with you everywhere you go is not very efficient. It's effective. It's, I'll tell you, you're grateful to have that metal around you in a nice warm car when it's minus 20 outside and the snow is blowing hard and it's dark. And, and it does that in Canada a fair bit, as you can imagine. Now, I wasn't driving the Spitfire in that weather, of course, because that was just a 2-seater rear-wheel drive. It would end up in the ditch backwards, in the snow. But for sure, you appreciate it when it's necessary. But that's the big deal, is that people are used to things, right? They get used to it. We're addicted to this notion that we can just drive and drive and drive and drive. And my Priuses have got a 600-kilometer range on a tank. And people get used to that. But I'll tell you, you can awfully easily get used to coming home and plugging your car in.
Well, and I think it's a bit like your mobile phone, though, as well. Some of the, before you were on a smartphone and your battery would last you, 3 or 4 days, and you'd plug it in every now and again, and then you'd go, well, if I had to plug it in every time I got home and plug it in every time I got back to work just to make my thing work, you'd look upon that as beforehand saying, oh, I don't know if I could do that. But once you've actually started using a smartphone, you're like, okay, it's well worth it.
Yeah.
Just to...
and just on that as well, like, so in Australia, obviously, we've got an abundance of sun, and solar is just, we've had an enormous, and we spoke before about some government intervention and whatnot. So I was having a quick look at comparisons between solar where you are and where we are, and we can install a max household size of about 6.6 kilowatts for about 2,500 in Victoria, where we are, and thanks to about half of that cost being filled in by the state government. I think up your way, and I'm not sure how prevalent solar is. I think it was about 13,000 Canadian dollars for a similar size system. But I guess it comes back to the fact that if you know that you're coming home and and obviously you probably need a battery at that point in time, but you're basically just using your energy from your house for the day to then fill up your car. That makes that transition period a lot smoother.
The thing we've got that you guys don't have is we've got huge amounts of hydro and nuclear.
Yep.
So in Ontario, our electricity grid is 40 grams of CO2 per kilowatt hour.
Do you know what it is here? I looked it up.
Yeah, it's 1,000?
Yeah, 1.13, one over a kilo. Yeah.
Yeah, exactly. 1,000, because you burn a lot of coal. There's a lot of rooftop solar on people's houses, which is awesome, and it's growing, and I love to see what's going on in Australia. I think it absolutely is headed in the right direction. But Ontario's already got that problem licked. We burned our last coal in 2013. Our grid's got a little bit of natural gas just to kind of counterbalance the wind power. There's only a tiny bit of solar, because the solar capacity factor here in Ontario is about 16%, whereas it's more like 30% in Australia, if I recall correctly. So, on an annualized basis, I've got solar panels that they're cheap here too. You can buy them from China, just like shipping costs a little higher, obviously. You can buy them cheap in Canada and have them shipped from China, and they're cheap enough. But the capacity factor is half. You only get half as many kilowatt hours out of a year out of the same nameplate capacity. So solar here is a bit rough. And the thing is, we're actually south of most of Germany, where I live in Toronto. So, a lot of Europe, it's really north.
Yeah,
you wouldn't think by the climate, but it's in terms of latitude, it's really north. And so solar is a bit rough. But wind is good, and the combination of wind and solar are awesome. The thing about Ontario, and more specifically, less specifically, thinking about Canada in general terms, 80% of us, round numbers, have access to a grid that's 40 grams per kilowatt hour or less. Like in Quebec, it's way less. In BC, it's way less. In Manitoba, it's way less. In Ontario, it's 40 because they've got abundant hydro resources. The thing that we haven't touched in Canada yet, which I'm scratching my head wondering what we're thinking, why we're not doing this, but we should be. And that is that our hydro, not all of it, some of it's run of river and whatever, but a lot of our hydro could be used to back up wind. So it could be used as kind of an in-place pumped hydro without the pump.
Right.
Yep. And, Quebec alone, just Quebec exports a tremendous amount of electricity to the northeastern United States. But Quebec, it's my understanding, I might have the stat wrong, but it's my understanding that Quebec has enough water behind its dams to run the Quebec grid for a year.
Right.
Okay. So, and that capacity, obviously, some of it you can't use because you can't run the reservoirs right down, and you can't have the rivers go from zero flow to full flow in 5 minutes or something like that. You'd end up causing all kinds of problems. But at the same time, there's a lot of capacity there to use that for storage that we're just not tapping into because I don't know, something wrong with us. We're not thinking very creatively, I think.
Or vested interest,
we'll
perhaps.
Get there.
There could be some vested interest.
I think it's people have boxes on their head, right? They're used to doing things a certain way, and if your grid's already awesome, why are you trying to make the grid better for other people? In the United States.
Yep.
I know why. Money.
Yeah.
If the United States was charging a big carbon tax, there'd be all kinds of Americans crawling all over Quebec going, oh man, we can put wind turbines all over the place here, and then we'll have this gigantic battery that's not free, but very low infrastructure cost and super high efficiency. Why aren't we doing this? Why weren't we doing this 10 years ago? It's a bit of a mystery, but I mean, we've got the same problems you guys have got. You have no carbon tax. We've got a federal carbon tax, which is awesome, but we've got, just like you guys have regions that have different politics. We've got provinces in Canada, and the provinces have their own governments, and our government leader, our dear leader, Doug Ford, is a closeted climate change denialist. And first thing he did when he got into power was he ripped up a whole bunch of renewable energy contracts, and he destroyed our functioning cap and trade system that we had working with Quebec and California. So, that's the trouble, is that these policies that are needed, they're absolutely necessary in order to make progress on decarbonization. But if they're not durable, then the investment community just looks at them and goes, why am I in this space? I can't make money. I can't guarantee that I can keep making money 5 years from now, because the government might change and they might just tear up everything.
Yeah, and
that's very frustrating.
Yeah, and that's been one of the big problems I've seen in the Australian. Although our solar power is actually is booming, and we're sticking lots of it on. There's been 3 or 4 times where you've had state governments go, hey, here's this great deal, and then it's gone. And then here's this great deal, and then it's gone. And each time they're doing it, they're saying, oh, what we're trying to do is we're trying to generate certainty for the local installation and all this other stuff. And they've done exactly the opposite, because they've given people, it's either flood or it's famine. Flood or it's drought, sorry. It's just like, and so the people who are doing it are like, no, I'm not going to set up my business to run this as an ongoing operation. I'm going to set it up as something where I can scale up really quickly when there's a good deal on, and then I can scale back again, and then I can scale up again. And so
this allocation
story of my customers' lives, actually. So what I do for a living is I design and build pilot plants for the chemical process industry. So they're pilot plants for every kind of process you can imagine.
So when you say a pilot plant, this is a scale sort of
a prototype,
proof of concept sort of thing. Yep.
Exactly. It's a tool that's used to minimize risk when you're scaling something up from the laboratory to commercial scale, to gather all the data and to make sure that you're not basically going to end up with something that build a giant plant for $1 billion and it doesn't work. That doesn't work out so well. So pilot plants are the mitigating factor in the middle, and that's what we do. But what tends to happen is that customers of ours will come in, and they're smart, motivated, hearts in the right place people, and they'll say, hey, we've got this great idea. We're going to make this thing, this compound or this material or whatever the case it may be. And we're going to do it in a way that generates less greenhouse gas emissions, or maybe none, or maybe even negative. And the only thing we need is a carbon tax in order to make it pay. And then once we achieve scale, we'll be making money hand over fist. So they bet that we will do that. They bet that we'll get serious about climate change, and we'll do something in the form of changing the broken economics that treats the atmosphere like a big, limitless public sewer that's free for CO2. They bet that we will fix that. We don't fix it, and they go broke. And it just happens again and again and again, and it's really disappointing. It's really unfortunate. And, we need those policy measures. And if you don't have them, you won't make progress on climate change. You'll make slow, pathetic, incremental progress, like people gradually putting solar panels on the roof and maybe batteries, and gradually buying electric cars because they like the instant torque like I do, but not because there's a cost imperative to do it that actually drives the real change. And not because there's a cost imperative that makes the investments to avoid those emissions worth making. The smart money's going to sit on the sidelines and go, yeah, wake me up when you guys are serious about this.
And so, I mean, getting back to some of these debunking, I mean, that was the other one I've heard, is that we can't switch everyone to EVs, because if we switch everyone to EVs, then
we'll run out of this or that.
We'll run out of our grid. And so so I've sort of done some rough numbers around that, saying, I guess using those similar types of ones, going, if the US needs 22 quadrillion BTU of oil to get, it actually only gets 4 quadrillion of mechanical energy for that 20% or 15% conversion. Actually, I was using, I think, 19%. So on a 15% conversion, it's even worse.
That's right.
And then you say, well, if electric cars are 77% efficient, and I think I was even using mid-60s, then you actually only need 7 quadrillion. So, and then the US...
Huge improvement.
Yeah, so maybe that comes back to 6 or something, I guess. And then the US is sort of 13. So you basically need to add about 50% to the US if you switch tomorrow. But you're never going to switch in 1 year. If you took you 10 years to get there, which is I would think incredibly optimistic.
Aggressive.
Yeah, like even if you started selling 100% electric cars next year, you've still got the existing fleet that's going to be around for the next 10 years anyway.
If you ban selling new ones, it's still going to take decades.
Yeah, and so I'm sort of going, well, you actually only need to add sort of 5% capacity to the energy system per year, and it's probably less than that. It's probably 3 or 4.
It is.
Yeah.
I think it's less than that. A guy named John Poljak, who's an Australian as well, did some calcs, and he published an article very recently where he looked at this, and he figured there's about a 25% increase in world electrical consumption to basically electrify all ground transport.
Right.
Wow.
Everything that's burning a fuel to move something around on the ground. Sorry, my apologies. I think that included aircraft too. I think so. I'm not sure. I could be wrong about that, but aircraft are only 2 or 3%. So not a giant deal. Whereas the rest of the ground transport's over 20%.
Yeah.
So 25%. And I did a calc, and the calc I did was a pretty simple one. I looked at the difference between daytime peak and nighttime trough consumption in Ontario. And I forget what the number is. I forget how many gigawatts of capacity it is, but I looked at the difference in average terms, and I looked at what percentage of our fleet could be electrified just by sopping up that excess electricity that right now is just not generated because they don't run the plants. Or, whatever it was that was generating that electricity during the day, they shut them off at night. And if they just kept running them, what percentage of our cars and light trucks could we electrify just on that difference? And that was 20%.
Wow. Right.
Now, that was 20% of the licensed vehicles, assuming they all drive. Okay. And in reality, there's an awful lot of licensed vehicles that don't drive. Like I've got a lot of mates who've got old British cars license that they drive to British Car Day once a year.
Yep.
And so if you figure that out, recreational vehicles and whatever cars that are just kind of there, but people aren't driving because they're elderly or incapacitated in some way, or whatever the case may be. Second and third vehicles, somebody's got a pickup truck just in case they need a pickup truck, and that they don't actually drive very often, or my buddy with his Star Trek themed van from the 1970s that he's got. The reality is it's probably 30% or something like that can just be done on the difference between daytime and nighttime capacity. Right. So in reality, I think it's even less. It's really electrification of transport, ground transport, especially cars and light trucks. And I honestly think heavy trucks are going this way too. Most of them, not all of them, but most of them, most of the joules of energy used by them anyway, are going electric. That is the lowest hanging fruit for decarbonization that there is, aside from other energy efficiency, like changing your incandescent light bulbs to LEDs and stuff like that. Most of which, here we've kind of already done the really easy stuff. So, but the way you get there is carbon taxes and emission bans. That's how you get there.
And so, I mean, that leads on to this battery thought that, I guess what I'm looking at is saying, getting that battery down to a cost where people start looking at their car and saying, okay, yeah, it's not that much more for a battery, and I'm going to save all this, I'll get my payback in 2 or 3 years. Okay, I'm in. And so, and battery costs have been falling at sort of 15-20% per annum. And you've written a little bit about some of the metal costs, I guess, that are going into, or the commodity costs that are going into the batteries, in terms of saying, okay, you won't be able to get that forever because there is this commodity cost, and so you can come down quickly.
There's an asymptote.
Yeah,
there's an asymptote. The cost curve cruises down, and it has to reach some multiple of the cost of the raw materials. And the raw materials, there is a bit of a challenge because the raw materials can actually increase in cost for a time because we don't have the capacity in the mines in order to produce them and in the refineries in order to produce the metals of the quality or purity that are needed. So there's going to have to be some investment needed, and that's going to cost some money, at least in the short term. So that's the the billion-dollar question, multi-billion-dollar question, is how low can batteries go? The amazing thing is they're already cheap enough. The problem is that people still have this ICE box on their head, right? They're used to the 600-kilometer range.
Mm.
So it's like, no, it's not a car if I can't drive it for 600 kilometers. Well, come on. I drove a car with a 100-kilometer range,
Mm.
16,000 miles,
Mm.
never ran out of juice once. The distance to work and back never varied, even with, blockages on the road and emergency trips to whatever and picking my son up from soccer or whatever the case may be. It never changed by more than 10 kilometers,
Mm.
And I had enough to almost drive there and back in
Yep.
a car with an 18.5 kilowatt hour battery pack. And I just bought some batteries from China and delivered to Canada. They were $100 a kilowatt hour. Now,
Wow.
they're not car batteries. They're lithium-ion batteries, but they're lower current capacity batteries that are meant for a solar application. I've got a little farm and it's off-grid, so I wanted a little bit more battery there so I can run my welder and the like. And a buddy of mine and I went together so we could buy enough of them to get a C shipment. Like, we're not buying a container load or anything, but we just went on Alibaba and we bought batteries for $100 a kilowatt hour,
Mm.
and they're 4,000 cycle life. And you work that out, that's 5 cents a kilowatt hour returned.
Mm.
And that's a battery I'm buying retail,
Mm.
not wholesale. I'm not buying, a gigawatt hour of them.
Mm.
I'm not ordering a factory mill run or whatever the case may be. I'm buying them retail at $100 a kilowatt hour. So it won't be long. Now that's not at the pack level. There's still some. You got to bolt these batteries that I bought are these prismatic cells, and they just have bolt holes in the top of the electrodes, and you just bolt them together with bus bars that are made out of copper. They're really simple to use. Building a pack out of them is costs nothing, and the battery management system that I'm going to end up using on this battery pack, I think it cost $2. I think it was $2. Yeah.
Wow.
So it's a board level device that I bought on AliExpress.
You sure you don't want to spend $4 and just make sure you don't blow up your battery pack, or is it not the way it works? That sounds too cheap, Paul.
Yeah, no, these are lithium iron phosphate batteries, and there's a really good video that was done by a company that I bought my lithium iron phosphate batteries that I used in my car project. They basically did a video, a bunch of guys at the factory in China. It's like, well, let's see if we can make these batteries catch fire. So they shorted them. They took a battery and they shorted it with a welding cable, to see if they could make it overheat. And they didn't make it catch fire. They fired like 3 or 4 pistol bullets at it. It didn't catch fire. They chucked one into a burning barrel, kind of thing that you see at strikes in the winter here in Canada, where you have just a 45-gallon drum full of burning wood. They chucked a battery in there to see if they could get a fireball out of it, and they didn't. So the lithium iron phosphate batteries, they're not idiot proof. You can still hurt yourself with them, but they're highly idiot resistant. So I'm not too worried about that. Now the nickel manganese nickel manganese cobalt ones, NMC ones, and the NCA ones that are used by Tesla and the like, that are higher energy density, they have a much lower onset temperature where they go bananas, and they catch fire on their own, and they're much sketchier. So there you'd want the $10 BMS for sure.
Yep.
Not the $2 one. Well, in fact, I am kind of pulling your leg a little bit. The BMS that I used on my car project, it was actually $15 a cell. So it added up to quite a bit of money. There were 33 cells in the car. But the one that I need for this little off-grid solar thing is much more modest because it's not very many cells in series. So I can use a board level device and it'll work great. And all it does is it just monitors voltage. If the voltage is too high, it shuts off the charger. If the voltage is too low, it shuts off the inverter. And there's also a temperature sensor. If the temperature is too low, it shuts off the charger. Done.
I mean,
not complicated.
I do find it's interesting as well that, and it's what we're talking about before about people are used to doing what they're used to doing. Because if you started today and you said, okay, we don't have any vehicles that travel, and we're thinking about going one of two ways. This battery one, where we're going to, it's a chance of overheating if you and issues on that side, or let's have a controlled explosion that we're going to control. We're going to have this whole energy sit up there. Let's put that on the front of the car, and then let's put a tank of highly flammable liquid as well. Let's do that way. That'll be much safer than this potential. You'd be like, no. I'm going
absolutely. The other way. Well, here's the kicker, right? Okay, so we've got one alternative that might be a little inconvenient if you wanted to go on a long trip, but for every other trip that you do, it's going to cost you half as much per mile driven. Okay, and no maintenance and whatever. And the other one will be a little bit more convenient, but it'll be more expensive per mile driven. Oh, and it'll also shorten your life. Like meaningfully shorten your life. Not because of fire risk or whatever, but because it emits toxic stuff out the tailpipe that people breathe, and it shortens their lives. So this is the thing, these combustion advocates, they do, my hat's off to them, because compared to the cars in the 1920s, we've really come a long way. But that's after a century, right? We've really come a long way in terms of the emissions. But I'm sorry, I don't want to let a combustion engineer tell me how safe he can make the air that I breathe in practical terms for enough money that I can afford in a vehicle. That's not a decision I want those people making for me. We have an alternative now that has no local tailpipe. It has no toxic stuff coming out of the tailpipe. Yeah, okay, it still has tires, so the tires wear, there's some particles from that. It still has brakes, but the brakes are used about 1/10 as much as the brakes in an IC engine car, because most of the braking is done by regenerative braking. So the brake dust emissions are tiny relative to those of a gasoline or diesel car. So in terms of total toxic emissions, an electric vehicle is a tiny fraction of what any combustion car is, whether it's a hybrid or not. And that's the facts of the matter. And the problem that we have, and this is really a frustrating problem with people, is that people don't make good choices. So if we have to take some of their choices away, that's the reality of it. And I know people hate to hear that. Oh, you technocrats and you elites, you're going to try to tell us what we can do and what we can't do. Well, damn right, we're going to tell you what you can do and can't do. Because if you let the market determine whether or not they wanted to buy gasoline with tetraethyl lead in it, that was cheaper, because that's a cheaper way to get the octane right so that the engine doesn't knock. Okay. And you gave them that choice, even though you put a giant sign on it that says, if you put this gas in your tank, it will give your kids brain damage, people would buy it.
That's cheap.
That's the reality of the world we live in. Oh yeah, I know it's killing my kids, but it's 30% cheaper, man. I got a budget.
It's an interesting point too, that if you sort of look into the future, petrol car drivers will probably be looked upon with the same level of disdain as cigarette smokers. In public places, perhaps might upset a few people in the audience. And oh god, at the end of the day, I guess if people want a V8, then they've probably got to drive it in the country or something.
Honestly, I think we have to be a little bit careful, because there are lots of uses for engines in the future, but they're for remote and rural transport. I mean, Australia is a country rather like Canada in that respect. You have a lot of far-flung places, and there are people that live there, and they need to live there, and they're going to keep living there.
Yep.
And they're not going to be well served by electricity for vehicles. They're going to need fuels, but we're going to give them biofuels.
Yeah,
that's how it's going to work. And those fuels are going to be very expensive. So the people that have to use them will use them, and those that don't won't.
Yeah. Well, and
That's how it's going to work.
and part of it, well, I guess that's my investment part. I've sort of got my investment hat on, looking at the whole that whole rundown and saying, okay, let's say we do start transferring across to and everyone starts buying EVs, and but you've still got these people running old electric cars, sorry, old petrol cars for a long time, and as I think you pointed out as well, you still got the refining that's still needed for plastics and jet fuel for a while, and all these other things. Is that I'm just not sure whether you get to the stage where you say, well maybe does it get expensive, or actually there's a bit of a byproduct already in most of these refineries that they're already pumping out whatever it is, 6 different things, and one of them happens to be a fuel that's acceptable to run a car, and so maybe it's a bit of a byproduct effect that the cost doesn't go up as much as you think, because they still need to keep making these other products. I don't know whether that's...
Oh, I see what you mean. Yeah, no, we're going to stop burning fossils as fuels. That's happening. We're going to stop it. So we're going to first stop with coal, and then we're going to stop burning petroleum. And the guy that came up with the periodic table, Mendeleev, pretty smart guy, knew a few things about chemistry, and I agree with him. He said that burning petroleum is kind of like burning banknotes in the kitchen stove to try to stay warm. It's a bad strategy. Okay, those molecules are too precious to be wasting as fuels. The fuel use is their lowest value use to humankind. A big part of my business is helping people try to use alternative feedstocks to make things that we're used to, that we need, that some things that we depend on for our very lives, like ammonia as an example. I mean, half the nitrogen in the protein in our bodies comes from Haber-Bosch ammonia that's derived right now almost exclusively from natural gas, because the natural gas is used to make the hydrogen that's used to make the ammonia, and there's no carbon capture going on with any of it. That's a huge problem that we have to solve. Okay. But with petroleum, the deal is this: about 25% of petroleum right now is used for non-fuels uses, and 75% is used for fuels uses. The 75% is going to stop. The 25% is going to continue. And we know already how to run refineries to make the products that we need in the future without making the fuels and without making CO2 emissions. All we have to do is have a way to make it pay. That means carbon taxes. That means emission bans. That's how you do it. And it will not happen unless you do those things. Okay. And the last man standing is going to be natural gas, and not such a big deal in Australia. Huge deal for us. Okay. Here in Canada, we're mostly heating climate. We burn natural gas 5 months a year here, sometimes 6. And then the rest of the year for our hot water and drying clothes and cooking and the like. And natural gas is so much cheaper than electricity when you use it to make heat as opposed to making electricity, that the cost per ton of CO2 that you avoid by switching from natural gas to electricity, even with a heat pump, it's really high. It's quite high in terms of the dollars per ton of CO2 that you avoid. Even on an awesome grid like we've got in Ontario, that's nuclear and hydro and wind, and only a little bit of natural gas, it's a very expensive transition to transition heating. And so that's the last one that's going to go, in my opinion. All the transport uses, they're going to go first.
Yeah, and so with the natural gas, then how much more expensive would it need to be before that equation didn't count? And I guess where I'm coming to, I'll tell you where I'm leading from this, is I look at the natural gas price in the US in particular and say, well, it's so low for me because it's a byproduct of the fracking process. And so, you're trying to get the oil, which is the most economically viable product, and you end up with this gas, and you say, well, what will I do with it? I'll sell it for whatever price I can get. And I guess what I'm wondering is if you tripled the price, for example, would that equation still work? Or how high would it need to get before, if you're not pumping the oil, not fracking for the oil, you don't have the gas so cheaply?
So there's an awful lot of hydraulic fracturing that's going on in the United States just for the production of natural gas. Okay. And there's a lot of hydraulic fracturing that's going on for petroleum production with associated gas, and the associated gas is being flared.
Right.
And that's being flared because a flare is cheap. Okay, a burner is cheap,
Mm.
and a pipe is more expensive than a flare. Can you imagine? In the continental United States. Now, in Canada, we've got rules that limit the amount of this that can be done, very strict rules. In the United States, there are jurisdictions that permit it, and they're doing it in giant quantity, and they still are. And it's a failure of regulation, and it's basically a crime against the environment that the whole world should be concerned about. The United States does not need to do this. It could fix it tomorrow by changing its regulations, and it fails to do so. So the reason I know about this is that I've had endless customers come to me with ideas of how to convert that natural gas into something that you could use, that you could sell.
Mm.
And the problem with doing it is that it's, any kind of chemical plant that you can make, especially a small one that doesn't produce very many barrels per day of product, or kilowatt hours of electricity, or whatever it is you're trying to make from that gas. It has a high marginal cost, and hence its economics suck. And it does not compete very well against a burner when
Mm.
there's no carbon tax,
Yeah.
right? So if you're competing against a burner which is cheaper than a pipe, no chemical conversion process is ever going to compete. So you just give up. You just don't do it, right? But all these guys are coming, oh yeah, we're going to do Fischer-Tropsch conversion. We're going to make, liquid products out of natural gas. And that's a process that you can do. People have been doing it since the 1930s, and it works. It's very inefficient, and it's very capital inefficient. And the only way that you can make it make money is if you get gas almost for free, but also in giant quantities. So, the Shell Pearl project in Qatar is an example of that. The plant is like a mile by a mile and a half, billions and billions of dollars. It's giant beyond imagination. There's two trains of 12 reactors, and each reactor's got 15,000 catalyst tubes in it, like mind-bogglingly huge. And that's just big enough to make money with almost free natural gas
Wow.
that the Qataris give them.
Right.
So, think about that. There's no way you're going to do that with small scale stuff out of a flare. The marginal cost of the equipment is just too expensive. But if when we start talking about $300 a ton carbon tax with a flaring ban, right? And now, if you want to go after that valuable, beautiful petroleum that's down there, it's light and sweet, and exactly what the market needs for this or that. And the only way you can do that is by not flaring and converting that gas into something valuable. Then all kinds of alternatives start to make sense, and we stop the waste.
Mm. But I guess where I was leading with that is, so whatever, we're sub $3, say, per MMBTU for gas. And what you're saying is it's not worth converting in terms of the heating benefit. If that was $12 instead of $3, would that equation still add up in Canada, or would you start saying let's start switching to electricity?
That's a hard one. I don't know for sure, because I don't know the ratio between my retail cost and the wholesale cost.
Yeah.
So, but what I can tell you is that gas would have to quadruple in price to make it make sense. It would have to double to break even if I didn't care about ever getting a payback.
Yeah. Yeah. Okay.
Now here's how you fix it. $150 a ton carbon tax fixes it right up. $150 a ton carbon tax makes a heat pump break even with a natural gas burner. And we're headed there in 2030. In Canada, we're going to be at 170 Canadian dollars a ton CO2 emissions. And the reason the population isn't revolting about this is the clever way they've done it with a matching dividend. And the population supports that. Let's hope that they don't vote out the government and screw everything up again, which is still a possibility. But if we don't, then I'm going to be in trouble, because I just installed a brand new gas boiler to heat my house, because my boiler killed itself in February, and I needed one quick. And I'm kind of hoping I can run that at least for another 10 years to make it make sense to have spent the money on it, because a heat pump would be rather hard to incorporate into my house, because I've got hydronic heating. But anyway, round numbers, it's $150 a ton that makes it break even. That varies greatly region to region, place to place, and how hard you heat, and what your relative tax burdens are. Then that's a problem all over the world, is that electricity is taxed unfavorably relative to heat. usually for reasons associated with concern about poverty and the like. So there's some structural stuff, on the government side that needs to be fixed in order to make that make sense.
Okay, sorry, and before we get to, thanks heaps for your time. I just wanted, getting to the batteries part. So I guess so for me now, the battery is the big cost, and that's the one which we want to see keep coming down over time, and it seems like we're getting incremental changes. I guess there was this part, we started talking about the asymptotes, and I think we sort of went off on a very interesting tangent, but let me come back to this one, is...
that's the way it goes when you talk to me, sorry.
That's all right. I didn't want to cut it off
tangents are us.
Yes. I guess where I was trying to get to is there seems to be a lot of different types of potential technologies out there, which seems to say, okay, well, if one mineral gets particularly expensive or another one gets particularly expensive, then you just switch to the next, what's the next one? So it doesn't mean that, let's say some people go, well, the cobalt price could go up 10 times higher and people still need it. It's like, well, no, because then they'll just start using these other technologies that don't use anywhere near as much cobalt.
Dead right.
And so the one I was sort of looking at is the solid state batteries, which I think some people are holding out as being, I guess, a step change in terms of the benefits. And so I guess the question is, are we going to go through this part about 15% cost reductions for the next few years, and then all of a sudden we might get a 50% cost reduction when solid state batteries hit the right level, or is that just another curve that we'll jump onto? I guess if I think about it, we're on this cost curve coming down, but there's a whole bunch of different technologies that are on their own cost curves, and then they gradually tap out. We have to go to the next technology and then the next technology before we get our entire curve down. Does that make sense?
Okay, so I'll answer that in a couple pieces. Okay, so I totally agree with you about the thrifting aspect. So if anything in particular, cobalt's the risky metal. Okay, that's it. That's the only one that's risky. And the industry's thrifting the heck out of cobalt right now. And the reason they're doing it is that cobalt's problem is not a lack of abundance. Cobalt's problem is it's abundant in the wrong country. It's abundant in a country that's dysfunctional and corrupt and desperately poor. And that's the Democratic Republic of Congo. And instead of trying to fix that country to make the poor Congolese better off, and allowing them to reap the benefit of their birthright in that incredible mineral wealth that they have, nobody can figure out how to fix the Congo, and they're not even going to try. So they're just basically writing off the Congo, writing off cobalt. And to me, it's kind of sad, but it's reality. So if cobalt gets too expensive, we just won't use it. The thing about solid state batteries is they're not going to be cheaper per se. That's not their big benefit. Okay. So the real reason people are after solid state batteries is they're safer. And by safer, I mean they have a potentially dramatically lower risk of fire, especially when you supercharge them, when you charge them at really high rates. And the problem with solid state batteries is threefold. Number one, they don't exist. Okay. So what I mean by that, and people go, what are you talking about? You hear about them all the time in the news. And that's true, but they don't exist. They fail Paul Martin's test of battery existence. Okay. You hear about all kinds of things in the news. Oh yeah, we've invented this brand new, wonderful technology. And in 10 years, it's going to take over the world. Right. And then you never hear about it again. And my test of existence for batteries is really simple. If it's a battery like a lithium-ion battery, as opposed to a grid storage battery or something like that, the test is really simple. After it's existed for 3 months in a commercial cell phone and it's worked great, it might be in cars a couple years later. Okay. So by that test, solid state batteries don't exist. They're not in anybody's cell phone. Okay. The other problem with solid state batteries is that they're harder to make. That's why they don't exist right now, because people can't figure out how to make them. By hard to make, I mean, not only is it hard to figure out how to make them work properly, but it's very, very hard to figure out how to automate the process of actually manufacturing them, because what's solid state about them is two things. One of them is the anode, which in a regular lithium-ion battery is graphite, that the lithium absorbs into when it's charged as lithium zero, lithium metal. In a solid state battery, it's a solid strip of lithium metal. Okay, so that has one implication is that all that volume that used to be taken up by anode graphite goes away, and you end up with just a strip of lithium. So the battery gets smaller, and hence the energy density goes up, and that's good. The problem is the amount of lithium per kilowatt hour pretty much doubles. Okay, so you need more lithium. But they're also really hard to make because the electrolyte, the other thing that's solid about them, is that the electrolyte in a solid state battery is a ceramic material generally, as opposed to a plastic. And in a regular lithium ion battery, it's a liquid, a combustible liquid with stuff dissolved in it, lithium salts dissolved in it. But in a solid state battery, it's basically a ceramic. And imagining how to process really thin layers of ceramic materials at high speeds to make thousands of anode cathode layers with electrolyte. It's tough. It's very difficult manufacturing to do. And so the process of scaling it up will take time, and it'll take bucket loads of money. The good news is there's a path to scale, and that path to scale is cell phones. Okay, the same path to scale that the liquid electrolyte batteries had. Okay, so they're not going to be cheaper. They're going to be higher energy density and probably faster to charge and way safer. That's their upside. Okay, their downside is they're going to cost more, not less.
Yeah.
For a long time.
Yeah. Okay.
Because they're harder to make.
Yeah, and I guess it's that thing, isn't it? That I don't know if that was from you or from somebody else. I was reading is that one of the real interesting things about batteries, how it works is in terms of the energy side, is that it works the same whether it's small or big. You know what I mean? Like there's the part where if I'm building a motor, an engine, then if I can build a really big engine, I get all these extra efficiencies versus having lots of small engines. Whereas batteries is effectively doesn't really matter whether you've got one small one or 1,000 all sort of strung together. It's effectively the same return. Is that right?
Right. That is kind of right, except that anytime that you have to stick 1,000 things together to make one thing, you'd be better off to make one big thing. Okay.
Yeah.
Now that's kind of a rule that sometimes has exceptions that more or less prove the rule when you think about them the right way. Like solar panels is a perfect example. No point making them any bigger than a certain size because they have to be handled by a person. So we're not going to make individual solar panels that are 20 feet by 20 feet on edge because it'd just be too hard to handle. But and that won't actually save you any money. But in terms of batteries, when you make a battery pack out of 7,000 cells like Tesla does, you pretty soon wake up and realize it would be way better to make them out of 500 cells if you could. With each of the cells being bigger, and it would be even better if you could make them out of 200. So that's one thing that Tesla has woken up to, and I was really pleased to see that because I'd been predicting that for years, that they would go to bigger cells, and that's what they're doing. They're having trouble. They're not getting there quite as quick as they'd hoped because they're trying to do several things at the same time. They're all good things, smart things. I've got a good article on LinkedIn about Battery Day and what they announced there. It's going to take a while to get there, but the point is that bigger's better. But the thing about batteries is that there's batteries for mobile applications, and then there's batteries for grid storage. And the thing about grid storage is that in grid storage, you want long periods of storage, so lots of kilowatt hours stored, and you don't need so many kilowatts of power. And so if you can use a battery that separates the power from the energy storage, that's actually a big benefit for grid storage.
So can you just expand on that, the difference between the power
Sure.
and the battery for us?
Yeah, absolutely. So a typical battery, lithium-ion battery, they give a current capacity in hours. Okay, so I'll use the numbers. So I bought some batteries recently, as I mentioned. They're 270 amp hours, and they have a maximum current capacity of 270 amps for 1 hour. Makes sense, right?
Yep.
So the power that they develop is determined by that C rate, that current capacity. Okay. But their storage is how many amp hours they have. And a car battery needs to have a really high C rate because you need lots of power to get you off the line. Okay. So you need lots of current at a given voltage in order to get you off the line. And then you also need storage in order to determine how far you can drive on a charge. But in grid storage, you don't really need very much power. Your maximum power draw in your house is not giant. It's nowhere near as big as a car will need in order to get it up to 100 kilometers an hour in a few seconds. So a grid storage battery for your home as an example, but it multiplied by that to be the grid, it cares more about the amount of energy storage and the cost per kilowatt hour that's stored or returned to you than it cares about the power that's delivered. And so batteries that can divorce those two things, one from another to optimize, will have a huge advantage for grid storage. So it makes sense that the batteries that we end up using for grid storage that are cheapest for grid storage, they're going to be different than car batteries.
Yep.
And the big one is flow batteries.
Yep.
So flow batteries are perfect for this, okay? Because the way a flow battery works is it's kind of like a fuel cell, except it doesn't screw around with hydrogen, which I don't believe in. We'll talk about that another day. But the battery itself is really just a bunch of anodes and cathodes, and the energy is stored in the electrolyte. And the electrolyte is just generally an aqueous solution, water solution of some chemicals in big plastic tanks. And for more storage, you don't need a bigger battery. You just need a bigger plastic tank and more electrolyte. Okay.
Right.
So you see how awesome that is for grid storage? Because you can divorce the power. The power just determines how big a battery you need. Okay. And the storage is just how much electrolyte and how many plastic tanks you have. So more storage is easy and cheap. And the great thing about these flow batteries is that the individual parts of a flow battery, they're just bolted together. So if one day your flow battery electrodes or membranes get ruined, their capacity is impaired because they've worn out, you can replace them. And the energy in your battery is still in that plastic tank. The electrolyte, nothing happens to it. It doesn't change. It doesn't go away. The problem with a lithium ion battery is that it's a sealed thing, right? And it's only got so much life. And when it's dead, you have to recycle it. Like when it's finally lost its capacity and it's on the steep slope towards its ultimate demise, then you have to recycle it because it has no serviceable components, no user serviceable components inside. It's a sealed deal. Once it's made, it starts degrading the second that you make it. So that's the great thing about flow batteries. Now they're not perfect. They've got other problems and their efficiency is not as good. And their big problem is they have no path to scale. And that's a real monster of a problem for the poor devils that are developing them, because there's no, mobile phone applications or laptops or cars or anything that to use them. So there's nobody willing to pay $3,000 a kilowatt hour for them at the beginning.
Right.
So their path to scale, you just basically have to have the deepest pockets in the world. There were these guys, Aquion, a few years ago that came up with a saltwater type battery. And they spent hundreds of millions of dollars trying to get to scale, and they went broke. So we're talking about billions of dollars to get one of these to scale. So it takes deep, deep pockets.
And so that was, so that's because that's where I was leading to with that was a similar part, but I'm just thinking through whether my question still makes sense to, because I guess I was thinking about that whole divergence part where, but I think you've probably already answered the question in terms of saying, I think certainly I thought of batteries as saying you improve the battery technology and some of it helps your house and some of it helps your car and your phone and everything all at once. But I guess what you're saying,
different technologies. They might even be just different ways of making a battery with the same stuff in it. Okay, so you can have, as one example, you can have a battery with lots and lots of layers that are really, really thin, and that'll give it really high current capacity, but it makes it expensive because it's got a lot of parts, right?
Mm.
Whereas if you make the layers a little bit thicker, the efficiency drops a little bit, and hence the amount of heat that it generates when you try to charge it or discharge it at a high current increases. But it's perfectly good for a grid storage application where the current demand is small.
Mm.
And
So,
that battery is cheaper per kilowatt hour, even though it's made out of the same stuff because it's got fewer parts.
yeah. So I guess what
Cool,
I'm
eh?
getting to
So they're
is
different.
for Tesla, making batteries for itself and Tesla making a Powerwall, is that going to I guess are you saying that the technologies behind that is just going to keep diverging, and so
They're using different technologies for those things right now,
yeah,
and they intend to use, even in the future, even more different technologies that are more different from one another than they're currently using. That's already stated clearly in the Battery Day presentation, that they intend to use these high nickel cells for the truck, their Class 8 truck, which I think is going to revolutionize the transport industry, because it's going to drop their energy costs and their maintenance costs tremendously. It won't do all of it, but it'll start at the short range end and it'll work inward. And biofuels will take the long range end, and there'll be nothing left for hydrogen in the middle. But the point is that Tesla is already looking at the appropriate cell technologies for each tech, right? So that the Powerwall, and the power pack, big grid storage type batteries, they're going to use a different technology, a different cell structure, and different cell chemistry than the cars. And the cars will use different ones from the trucks, and the cars in China will use different ones from the cars in America, where people, have a few more dollars in their pocket. Um, so you'll have a battery of the same physical size, but it'll have lower capacity in China than it will in
Do
the
you,
States.
Paul, do you see Tesla heading down the flow path to
No,
do those?
flow batteries are useless for transport. Totally
Oh,
useless for transport.
Apologies, not for their cars, but for their static
For
energy Powerwalls.
grid storage,
Yeah.
you never know what Mr. Musk has up his sleeve, but I have no indication that they're interested in flow batteries at all. However, there are some big companies, I can't tell you who, but I know there are some of them are my customers, that are working on flow battery technology that's quite interesting. And some of these people are heavy hitters, and they're not from the battery industry. That's what's interesting. There are people that are just looking at it and going, this is an energy problem. We know all about energy. We know about technology. We know how to do technology development, especially if it's chemical. And so this is a problem we can take on, and they're taking it on. So it's going to be fascinating to see what happens.
Absolutely.
Exciting time.
Excellent. And you've alluded to, but I'll do probably, I'll only do 30 seconds or a minute on this, but because I know that we sort of want to thank you for your time, and I bet we could talk for another hour and 20.
Sounds like a whole other show's coming. But
I guess I'll
Yeah,
point
we
people
could.
to your
Yeah.
I'll point people to your hydrogen article on LinkedIn. But just your thoughts, the 2-minute version of the hydrogen.
Oh yeah, sure. So hydrogen, the thing about hydrogen is that hydrogen is not only not a decarbonization solution, it's a giant decarbonization problem that we haven't even started to solve. And it's so important that we solve it, that our lives literally depend on it. I mean, half the people on the planet are wouldn't be here if we didn't have a way to make hydrogen right now, uh, economically, to make ammonia. So right now we do almost all of the hydrogen production in the world. 98.5% by my estimate is made from fossil fuels, either natural gas or coal, without carbon capture. And that hasn't changed in 20 years, and it's not changing now either. Okay, you hear tons of hype. It's motivated. It's being put forward by two groups of people. It's the fossil fuel industry and their useful idiots. Okay, so the fossil fuel industry and the people that sell natural gas, produce natural gas, distribute natural gas to users, They see the writing on the wall. They see their future coming to an end one day, and they need to have something to sell. So they're reaching around, and hydrogen's it. So they're pushing it hard. And the useful idiots are the electrolyzer guys and fuel cell guys, and to some degree the wind and solar people as well, that seem to think that there is this hard to decarbonize part of industry that can only be fixed with molecules instead of electricity. Now, here's the interesting thing. I've been making and using hydrogen and syngas for 30 years, and I don't believe that hydrogen is a decarbonization solution. I think using it as a fuel is always fraught with difficulties and cost. And the real kicker to hydrogen is that we will often trade efficiency for effectiveness. I mean, that's gasoline in a car. It's inefficient, but man, it's super effective. It's a liquid fuel. It's not all that expensive if you don't have to worry about CO2. But hydrogen is neither efficient nor effective as a fuel. That's why we don't use it as a fuel at all in the world. We don't use it as a fuel. So these people that are trying to sell it to you, their motivation is questionable because they know this too. Okay. It's not something that I know magically and they don't know. They're selling it to you. You shouldn't buy it. So, the standard sales pitch that you get is that renewable electricity is going to be so cheap and we're going to make so much of it that we're going to have all this electricity that's just going to go to waste. And why not convert it into hydrogen and it'll be great, right? And the problem with that notion is that it sounds good on the surface until you look at the economics. The problem is that the things that you use to make hydrogen out of electricity and water, the electrolyzers, those things are not only not free, but they're not cheap. They're super expensive. Now, if you make more of them and you make them at larger scale, they'll get cheaper. That's true. Will they get cheaper by a factor of 100? That's what it would take to make them cheap enough to use just the curtailed electricity to make hydrogen. They have to drop in price by a factor of 100, not 10. Okay. Even to make sense at using the full output of new wind and solar resources to make hydrogen, they have to drop in price by a factor of 10. Now, that might happen one day, okay, but it won't happen without somebody providing tens to hundreds of billions of dollars to buy hydrogen from expensive electrolyzers that aren't cheap enough yet. Okay, so you have to buy your way with subsidy into this cheaper price. And hydrogen is on its third round of what I've been calling hopium addiction in recorded memory. There was a big push in the 70s after the energy crisis, and then there was a push again in the late 90s, and I was an active part of it. I worked for clients like Texaco and Chevron, trying to make hydrogen for fuel cells to first feed vehicles and then to do combined heat and power in homes. And it was clear to me what the problems were even back then, and nothing's changed. And now it's happening again. Yeah. And if this was all private money, I'd be totally behind it. I'd say, you know what, guys, knock yourselves out. It's great, go for it. It's not. It's not private money. It's public money they're after.
Yeah,
and that's what makes me so mad about it. It's crazy.
Yeah, and the big picture thing, is that solar panels have been working for whatever it is, 50 years or 60 years, and just every year they get cheaper and cheaper and cheaper. But as you said, we've been at this hydrogen problem for roughly the same amount of time, and you still haven't got things out there that are working and anything to show for it. Yeah.
For longer. We've known about fuel cells since the 1850s. At least, right. And electrolysis at least the same amount of time, because it's just the reverse. And the challenges with hydrogen's fundamental problems are thermodynamic and the properties of the hydrogen molecule, and they're not changing. Yep. The absolute bleeding edge best case cycle efficiency to take electricity and go through hydrogen and store it and then come back out with electricity again is 37%. A dime a dozen lithium ion battery does 90+% on the same basis, okay, with less fuss and muss, and it doesn't need giant scale to do it either. So it boggles my mind. But I do see a lot of motivated people, and my good friend Alex Grant, who's a lithium ion guy, lithium materials guy, he and I wrote an article where we call it for what we think it is. We call it the fossil fuel industry's last grand scam.
Mm.
The basic idea is people that have natural gas assets in the ground, whether they be distribution assets or actual gas or gas processing facilities or whatever, they need you to believe that they're worth money in a decarbonized future.
Yep.
And hydrogen is their way to get there.
Mm.
Now, that's not green hydrogen. Green hydrogen is just the bait, the hydrogen made from electricity. That's just the bait. They don't believe in it.
Mm.
So if carbon taxes come along, what they'll do is they'll take their black hydrogen, which is 30% blacker in CO2 emissions than the methane it's made out of. Okay. And they'll gradually make it kind of a muddy blackish blue by burying some of the CO2 when the carbon taxes get high enough. So they'll be selling you bruise colored hydrogen. It's kind of insane, the whole thing, because people are talking about there being this move to, we're going to use gray. They call it gray hydrogen, even though it's ultra black. These colors of euphemism just drive me nuts because they're so effective and so wrong. But they're going to take their ultra black hydrogen and they're going to gradually bury some of the CO2 over time. That's their game plan. And people have this idea that oh no, this is just a transitional thing. Well, that's not how capital works, guys. You don't build a steam methane reformer plant that will last easily 30 years unless you think you can get 30 years out of it.
Yeah.
Okay. And by the way, people are still building those plants, not talking about it, not MOUs, not announcements, not ribbon cutting ceremonies, not holding their hand out for funding. They're building them. They're building a giant new SMR, biggest one that Air Products has ever built in Texas City, $1 billion ammonia plant with a giant no carbon capture SMR feeding it. They're building a similar $1 billion methanol and dimethyl ether plant in Trinidad and Tobago, under construction right now. Numerous $1 billion facilities are being built in the world, making the same black stuff. That is the only stuff you can buy. It's the only hydrogen you can buy right now. So what you're being sold is a bill of goods, and the people that are creating the bill of goods, they've got an invoice for you. It's waiting.
Yep.
So my suggestion is we don't buy into it. We use electricity instead, rather than going through this lossy multi-step middleman of hydrogen, because it's neither efficient nor effective. And my article will give you all the facts and figures and all the numbers and the references and spell it all out for you. Or you can listen to the Redefining Energy podcast, where I've talked about this a couple of times with some smart guys who look at it from the finance side, whereas I'm looking at it from the technical side, really. But
Yep.
it doesn't add up. It doesn't make sense to me.
Excellent. That's been an action-packed show, and I think there's plenty of stuff there. We'd love to get you back on sometime to pick away at some other threads. But yeah, just want to say thank you very much, Tim.
Good on, yeah,
Very
good on
welcome.
you, Paul. Yeah, no, look, great to have you on. Would you like to share with our audience? And obviously, we're going to put some LinkedIn posts up as well, just to help colour in for our audience in our show notes as well. I enjoyed it's a little bit of a rabbit warren of articles that you've got there, where one feeds into another one that feeds into another one before you know it, it's midnight. So you terrific articles. I honestly, I can't recommend them enough. You get your point across so cleanly. It's kind of like XKCD. The guy that does all the mathematical equations and everything, but this with some personal anecdotes as well. So, that's
a giant compliment. I thank you so much for saying that. I see myself as having kind of a role in the middle between the science popularist guys who just want to, give you the most basic understanding of how things are going and how they're working, and the technical paper that gives you the nitty-gritty detail. I try to be in the middle somewhere, and still be, somewhat amusing. And I call a spade, or in fact, generally I call a spade a shovel, because that makes it clearer. And I don't pull my punches. So that makes it fun reading, unless I'm saying something that you don't agree with, then it makes you mad. And that's okay too.
Well, it's not even something we've got a vested interest in providing. Doesn't matter if we agree with you or not. We might know that it's wrong, but if it's a vested interest, then we need to get stuck into you.
Now that's the other thing. People will call me up. I do private consulting in relation to these matters. If it's anything to do with pilot plants, of course, it goes through my employer. But people will call me up and engage with me in private consulting because, and these are smart people, and they do this to make sure that they're not drinking too much of their own bathwater, so to speak,
Mm.
right? Because when you're doing something with money and you believe in it, but you want to make sure that it's right, that you've got it right.
Mm.
Sometimes it pays to spend a little money talking to somebody who's skeptical about what you're doing to see if you've got all your bases covered. And sometimes these guys do. They've got a niche or they've got a play that makes some sense. And if I can't poke holes in it, then they know that they're on the right track. But sometimes it's like, oh, geez, have you thought about this? And it's like, oh, oh, it sounded like such a good idea. You know, that's my specialty, is finding that deal killer in 5 minutes.
It's being the downer, being the.
I am Debbie Downer. That's me.
Yeah, but I mean, and look, that's actually the exact way we look at a lot of our investments as well. Is we're a big focus on our investments in terms of saying, right, let's we've got to sort of our models throw these companies up and say, okay, you should buy these companies because of all these reasons, and then we spend all that time fundamentally going, no, that must be wrong, and then eventually you go, I can't find a reason why it's wrong. I guess I have to buy that stock, and then it goes in.
Yeah,
so
I hear you. My problem, of course, is that I'm so skeptical that sometimes I will miss that thing that everybody else sees in terms of an opportunity, just because it just seems a little bit too hopeful. So I do have a bit of a bias that way. I am kind of a Debbie Downer, but the fact of the matter is, and this is the interesting part, whenever you're looking for advice in talking to someone, what you need to worry about or concern yourself with, not really worry about, is whether or not the person that's offering you advice is in a moral hazard position. Okay. So what I mean by that is that often advice is given by people that profit from your attempt, whether it succeeds or fails.
Yes.
And those people are in a moral hazard position. So if someone comes to me in my capacity as a guy that designs and builds pilot plants and says, hey, I've got this chemical process technology and I've got a bucket load of money from investors, should I pilot this thing? My answer is going to be, well, yeah, of course you should. Yeah, absolutely. When can we start? Right? Like, we'll do a great job of it for you. It's, I'm the wrong guy to ask, does it make sense? Will it make money? Is the idea a good one? But if you come to me privately and you say, I've got this idea and I want to turn 1 million sow's ears into a single silk purse, I can say, well, market price for silk purses isn't high enough to make that pay, guy. I'm sorry. It just doesn't make sense.
Yeah.
Don't do it. Find something else to do.
Yeah, and that's to bring back to investment. That's exactly where we designed our own. As we're doing our own, usually running a bond portfolio is actually really cheap, and running an international equity portfolio is very expensive. And so, if you price it to your customers as saying, okay, I'm going to charge you 1% to do your international equities and 20 basis points to do your bond, and then people say, oh, which do you think I should buy? It's like, oh, well, why don't you buy our international? International. All of a sudden, you've got this whole thing about always buy international equities because we make 5 times as much. And so we've sort of gone, okay, well, let's actually bring all the costs down to one. So at least you can say, okay, yes, we know we're definitely overcharging for these doing the bonds, but we're undercharging for these. But at least when we tell you to buy international equities, you're not sitting there going, is that just because you're going to get 5 times as much money from us? Yeah.
Now, this is the thing with me. People will often, it's quite funny, they'll try to impeach my opinion on the basis of some perceived conflict of interest.
Yes.
Okay?
Play the man, not the ball.
Yeah, that's fun. Fun thing to do. It's, never attack the idea, attack the guy, right? Because attacking the idea requires you to actually think about it and, make good arguments. And attacking the guy, you can just say he's an idiot and he'll get mad and go away. But the thing is that I'm often accused in the same day by people on one side of a debate, and then by guys on the other side of the debate, of having diametrically opposite conflicts of interest, and I don't have either. I'm not involved in any of it. I don't own any Tesla stock, for instance. I think that stock its value is controlled by irrational forces, and it's not an investment for me. It doesn't mean it's not an investment for anybody. It just means that for me, it's not an investment. It looks much more like a gamble in either direction. But I don't give advice on those sorts of matters. What I do is I look at it and say, well, the technology looks like this, and I'm doing it from the perspective of a guy that has fossil fuel customers, and has biofuels customers, and has battery materials customers, and has customers that are doing things that I can't even talk about because the lawyers would be after me, because they're so interesting and tied up by non-disclosure agreements. So I can't even talk about them. But there's no conflict of interest in there in relation to a particular technology that alters my opinion. I'm just old enough now, and I've got kids, and I worry about their future, and I want us to seize with this problem of global warming and deal with it, because I've been so disappointed, because I knew that this was a problem when I graduated from university, and I figured that we'd be well into solving it long before the later stages of my career, after I've been at it for 30 years. And it's so disappointing that we're not there. We haven't done it, and we got to get at it. The technology's there. We don't need to invent anything. There's no magic Deus ex machina thing coming from the sky to solve all our problems for us. It's not going to happen. We have to put the economics in place and the regulatory controls in place and be serious and get on with it. And then, you know what? The technology, the inventions will come. People like me and my customers will take care of it. But we need the driver. We need the driving force. And if you don't have it, if you don't have the carbon taxes, you don't have the emission bans, you can't do it. You're expecting something for nothing, and that's hard to find.
Yep.
That's an excellent note to finish on.
It is.
Thank you.
Well
All right.
put. Lovely.
Anytime, guys. It was really fun.
Yeah, look, great to have you on. And we'll look forward to getting you back on the show really soon. So all the best. And until then, cheers.